So we talk here about section 4.2, the mean value theorem, known as the MVT. And as you know, this is a big one. So let's make sure we're clear on the conditions. What has to happen before we can use the mean value theorem, and what exactly does the mean value theorem tell us? So it says if f of x, if we have a function that is continuous on the closed interval a, b, and differentiable on the open interval a, b, then there must be at least one value c in the open interval from a to b, such that f prime of c is equal to fb minus f of a over b minus a. Sometimes we say that the instantaneous rate of change must equal the average rate of change for some value of c in that interval when the function is continuous on the closed interval and differentiable on the open interval. Visually, what that means is if we have this yellow graph here from A to B, which we can see is continuous and we can see is differentiable because there's no corners or cusps or sharp turns. Then if we look at f of b minus f of a over b minus a is the slope of that line between the points a, f of a, and b, f of b. The mean value theorem says there must be slopes of tangents that are parallel, that are the same slope, so tangent lines parallel to that secant line somewhere between A and B. And if you kind of visualize, I think you can see there's going to be one there, so that would be one value of C. And I think there's going to be yet another one over here, so there's going to be, in this case, a second value of C, where the derivative is equal to the average rate of change. The instantaneous rate of change is equal to the average rate of change. Now, if the function is not differentiable, like we see in our absolute value function, then it doesn't work. Then the mean value theorem doesn't apply, because as you can see here, here is your f of b minus f of a over b minus a. It's going to be a line that has slope 0, but there is no point on that absolute value looking curve that has a derivative of 0. That's not, a violation. That doesn't show that the mean value theorem isn't true. It just shows that this function f of x here does not satisfy the condition of differentiability that we need. Now, Rolle's theorem is kind of crazy. I just can't believe Rolle gets his name attached to this, because if I was just born a little bit earlier, this could be the Street's theorem. Because if you know the mean value theorem, Rolle's theorem is just like a small step up from that. So Rolle's theorem has the same conditions initially. F has to be continuous, it has to be differentiable, and it adds the condition that f of a, some people say it differently. Some people just say f of a has to equal f of b. Our book goes on and says they both have to be 0. Then, well, you can see that if f of a is equal to f of b, then this is really saying, the mean value theorem is saying that the derivative must be equal to 0. Rolle's, whoever Rolle is, claims that and gets his name on that theorem. Unbelievable. Tell you what, it could be Street's theorem. I was just born at the wrong time. Anyway, I'll let that go. I'll try to anyway. Let's use an example here. Here's f of x equals x squared plus 4x plus 3 on the interval from 0 to 2. Show the MVT applies. So we can see that this function is a polynomial, therefore it's continuous everywhere and differentiable everywhere. If we figure out that f of 0 is going to be just 3, and f of 2 is going to be, let's see, 2 squared is 4 plus 8 plus 3 looks like 12 plus 3 is 15. So our f of b minus f of a over b minus a is going to be 15 minus 3 over 2 minus 0. That looks like 12 over 2, which is 6. So there's f of b minus f of a over b minus a. And the claim is that the derivative must equal that somewhere between 0 and 2. So f prime of x we can figure is 2x plus 4, we set the 2x plus 4 equal to the 6. There's our f prime equal to fb minus f of a over b minus a. We can solve that easily enough and get x equals 1. We can see that 1 is indeed between 0 and 2, so our value of c guaranteed by the mean value theorem is c equals 1. Okay? On to the next panel. Why does the mean value theorem fail to work for f of x equals this piecewise function on the interval from -1 to 1? Well, let's see. What is, we need to see, is this continuous and differentiable? Well, to get the continuity part, so to be continuous, we need for the left-hand limit to equal the right-hand limit to equal f of 0. So our left-hand limit, if we plug in the 0 into that left branch, we're going to get 0 squared is 0. When we plug into the right-hand limit, the 0, those look okay. And when that's also the value of the function there is in that right-hand branch. So we check off the continuity piece on that interval from -1 to 1. Now to get the differentiability piece, we need the left-hand derivative evaluated at 0. Well, the left-hand derivative, if we, let me erase that equal sign. So the left-hand derivative is going to be 2x evaluated at x equals 0 is 0. But the right-hand derivative is 1 everywhere, and so since the left-hand derivative is not equal to the right-hand derivative, what we really have is a corner point here at x equals 0, and that is not differentiable. And so we have not satisfied the conditions of the mean value theorem. And we'll see then that at f of -1, that's going to be -1 squared is +1. F of +1 is just x, which is 1. So the f of b minus f of a over b minus a is going to be 1 minus 1 over 1 minus -1 is 0 over 2 is 0. And you can see that since our derivative is 2x, but that's only for x less than 0, and our derivative here on this branch is always 1, the derivative f prime of x is not equal to 0 anywhere. But we know that we're not held to that result because we failed to satisfy the conditions of the mean value theorem. Okay, so our definition here for increasing, decreasing functions means that, and notice that it's a condition on an interval. Sometimes we get a little bit careless and we talk about is a function increasing or decreasing at a point. And well, it's really a property of an interval. So we would say that a function is increasing on an interval when as the x values get bigger, so do the y values, and it is decreasing on that interval if as the x values get bigger, the y values get smaller. And remember that we include the endpoints on an interval where the function is increasing and decreasing as long as the function is defined there. We have a theorem which is not, I think, too earth-shattering, but one that we make huge use of. So we say if the derivative is positive, then the function is going to be increasing on that interval. And notice that we don't have to have the derivative be positive at the endpoints as long as the function is continuous on that interval. And likewise, a negative derivative is going to mean it's decreasing on that interval. So let's do an... So here we have the function f of x equals 12x minus x to the third. We're going to find where is it increasing and decreasing. So this is a derivative question. We take the derivative and get 12 minus 3x squared. Remember, we're going to set that equal to 0. So we can factor out the 3 and think of that as 4 minus x squared. And we can see that this will be equal to 0 at x equals positive 2, and negative 2. So these are what we call our critical points. Remember, we look at a number line, and what we know is that the only place where the derivative can change sign is where it's equal to 0 or undefined, and there's no places where it's undefined, so it can only change sign at negative 2 and 2. So that means the sign of the derivative will be the same everywhere on this far left region. If we plug in a representative from this region, say a negative 3, then we can see that the negative 3 squared is going to be 9, and the 4 minus 9 is going to be negative, and a positive 3 times a negative is going to be negative, so it's negative in this interval all the way from negative infinity to negative 2. If we plug in 0, we can see we're going to get a positive, and if you plug in a positive 3 or anything bigger, we're going to be back to negative. So from here, we get that the function is going to be decreasing on the interval from negative infinity to negative 2, including the negative 2, and also on that interval from 2 to positive infinity. And it will be increasing on that interval, and we include both the negative 2 and the 2. So even though it seems kind of weird, negative 2 is part of an interval where the function is decreasing, but it is also part of the interval where the function is increasing. The next theorems I don't think are too earth-shattering. It says here on this theorem that if the derivative is 0 over an interval, then that means the function must be y equals a constant. The next one says that if two functions have the same derivative, that doesn't necessarily mean the functions are equal to each other, but that they could be different by a constant. And for example, if we have a function whose derivative is 2x, then we know that we're looking for a function now whose derivative is 2x, and that can be x squared plus any constant, since the derivative of a constant is 0. If it also contains the point 1,5, that gives us a way of solving for that particular constant. We can put 5 in for the y value and 1 in for the value of x, and get that that constant is 4. That means that the actual function that has derivative 2x and also contains the point 1,5 is going to be x squared plus 4. So we now, if we didn't know this already, this would be adding to our vocabulary, but we're just refreshing our memories and brushing off the cobwebs. So if a function capital F of x is an antiderivative, we say a function capital F of x is an antiderivative of little f, if capital F prime equals little f for all those values of x in the domain of little f, and that process of finding capital F is known as antidifferentiation. So our example, find the velocity and position function of an object that has acceleration negative 9.8 meters per second squared, initial velocity v sub 0, and initial height s of 0 is equal to h sub 0. So we're saying then acceleration is the second derivative of position is negative 9.8. So then we can anti-differentiate both sides and get s prime of t, which is otherwise known as the velocity, is going to be a negative 9.8. Whoops, I put the decimal point in the wrong place. Let me fix that. It's a negative 9.8 t plus some constant. And we know that the velocity at time 0 is, we're calling that v sub 0. That's going to be our constant. So that means we have that our velocity, or s prime, is going to be a negative 9.8 t plus this v sub 0 initial velocity. We anti-differentiate both sides, getting us to our s of t. And when we look for the function whose derivative is t, that's going to be t squared over 2 times the negative 9.8 makes that negative 4.9 t squared, and then integrating, or we can anti-differentiate the v sub 0, makes that v sub 0 t plus a constant. Since our initial height or position we're told is h sub 0, then that makes our actual s of t, our position at time t, negative 4.9 t squared plus v sub 0 t plus, what do I call that, h sub 0? So let me call that then h sub 0. All right, very good.